This is the second part of lesson 8.8. Continuing in our lesson on number 4, we're now going to move to the proof part. And so if you remember before when we've done proofs, we've done a lot of two-column proofs where you have a statement and you have a reason. And so all of your reasons are things like definitions and theorems and things like that. However, you do proofs all the time in math just when you show all of your steps to working through an equation. So every time you show your steps of how you get from beginning to end, that in and of itself is a proof. And so what we're going to be doing here for this type of proof is we're just going to be working on one side of the equation to make it look like the other side. So one really important thing to remember is that when you're proving that this side is equal to this side, you've got to choose a side. That's the one you're working on. Do not mess with the other side. What happens is if you start messing with this side and you start messing with this side, you might have two completely different things, and if you've messed up both sides, who knows if it's right or not. So let's just choose the most complicated side. That's the way you want to do it. It's easier to go from complicated to easy than from easy to the millions of complicated things it could be. So one can be written billions and billions, infinite number of ways, but the expression that we have on the left, I'm going to try to make that one so I know what it needs to look like. And so just focus on the most complicated side and work to make it look like the other side. So again, just like when we were simplifying our expressions, that's really what we're doing here. We're looking to simplify this expression. So just focus on this and look at what you know. So one thing I noticed that this is a binomial. So if I had something like x minus 2 times 2 plus x, if that was the question, I could distribute. And so I can do exactly the same thing here. The thing is, when you're doing this, you're not really doing very many new skills. They look different because it's secant and tangent instead of x or x squared, but the skills are not really new. So looking at this distributing, I'm going to have secant x times secant x. Before we write that down, let's go through a couple of things. And I'll use cosine to do this. If I have cosine squared theta, that means cosine theta times cosine theta. You could also write it as cosine theta squared. What it is not equal to, it is not equal to cosine theta squared. This one right here means you're taking the input and you're squaring it and then you're taking the cosine, so it's an order of operations issue. On all of these other ones, you're taking the cosine of the input and then multiplying it by the cosine of the input. And so that's two different things. And so when we talk about cosine squared theta or tangent squared theta, we're talking about the cosine or the tangent or the secant or whatever being squared, not the theta. So as I do secant x times secant x, that's going to be secant squared x. Then I'm going to do secant times tangent, and it's positive, so I'm going to say plus secant x tangent x. Then I'm going to do negative tangent times secant. And remember, when you're multiplying, the commutative property applies here. So I'm going to write secant x tangent x. You'll see why in a second. And then I'm going to do negative tangent x times tangent x, so negative tangent squared x. Now, if you look at that, what do you know about this? And so think back to when we were doing something like x plus 1 times x minus 1. When you multiply that together, you get x squared minus x plus x minus 1. And what did we do with those middle terms? It's exactly the same thing right there. Like I said, not a lot of new skills involved here. In fact, I don't think that there's any new skills involved in this whole lesson. It's just that they look so much different and they're so much more complicated just because they look different. So this is going to be canceling out because you're taking secant tangent minus secant tangent. So it's all gone. So what you're left with is secant squared x minus tangent squared x. Okay, now remember my strategy I told you earlier. Put everything in terms of sine and cosine. So secant squared is going to be 1 over cosine squared x minus, and then tangent squared is sine squared x over cosine squared x. And so then if you look at that, what do you notice about the denominators? They're already the same, so I can just put this together in one fraction. And then you need to notice the numerator. what do you know is equal to 1 minus sine squared x? So think back to what we did at the very beginning of the lesson, Pythagorean identity. Remember that when we talked about cosine squared x plus sine squared x equals 1, if you subtract sine squared x from both sides, you have 1 minus sine squared x is equal to cosine squared x, so this is what I've got. And any number divided by itself is 1. And so what we've just done is we have shown that what we started with is equal to 1, and that's proven. Okay, number 5. We're going to prove that cosecant theta times tangent theta is equal to secant theta. So which side is the most complicated? This side on the left, it has more ratios. It is at least as complicated as the right-hand side. So we're going to just work on the left-hand side. So go back to the strategy of write everything as sine and cosine. So pause the video and write this in just terms of sine and cosine. Remember that you're not messing with the right-hand side, so don't do anything to the right-hand side, just on the left-hand side. Pause the video and then come back and we'll talk about how to do this. Okay, cosecant theta is 1 over sine theta times tangent theta is sine theta over cosine theta. And you're just multiplying this. So since it's multiplied, you can cancel factors, and so you've got that. So what you have left is 1 over cosine theta. And what is 1 over cosine theta? It is secant theta. And there you have proven it. That was a pretty easy proof. But again, this strategy of putting everything in terms of sine and cosine is a really, really good strategy. Okay, number 6. Prove cotangent. This is alpha. It's a Greek letter, and again, it's just an input variable. So cotangent alpha plus tangent alpha divided by tangent alpha, prove that that's equal to cosecant alpha. So the left-hand side, hopefully that looks more complicated to you. It does to me. So we're going to work with that. And so again, notice that you've got this fraction bar right here, and this is going to be a complex fraction because you're going to have a fraction divided by a fraction. So let's go ahead and write it all out, and then we'll focus in on just the numerator, and then we'll just focus on the denominator. So cotangent alpha is cosine alpha over sine alpha plus tangent alpha is sine alpha over cosine alpha. Then we've got our fraction bar, and then we're going to have our denominator as tangent alpha, so that's sine alpha over cosine alpha. Now remember, you cannot cancel those, and you cannot cancel those. So let's just look at our numerator, so just the blue part, just that part right there. And we're going to find some common denominators. So if you look at your denominators, you've got sine and cosine, and so your common denominator is going to be sine alpha cosine alpha. So to make that happen, I'm going to have to multiply this one by cosine over cosine, because you have to multiply by 1. And then this one I'm going to multiply by sine over sine. And so my first equation right there, I'm going to have cosine squared alpha. And then this one, I'm going to have sine squared alpha, and they're being added. Okay, now let's go to the denominator. So sine over cosine, there's nothing to do there, and so I'm just going to leave that. Okay, now look at what's in green. Okay, so this part right there, do you notice what have we learned about cosine squared plus sine squared? So remember that that's equal to 1. So my numerator is that. Okay, that's what the numerator is. Now as far as dividing by my denominator, when you divide by a fraction, that is the same as multiply by the reciprocal. See, not a new skill. And so now I'm just multiplying these two terms, and I can look at their factors and I can say, oh hey, I'm going to cancel that, because I can do that because they're factors. There's no adding or subtracting here. So what I have left is 1 over sine squared alpha, and 1 over sine is cosecant, so this is cosecant alpha, cosecant squared alpha, and I have just proven what I set out to prove.